Today we're going to talk about the second part of trig integration. As if you've noticed, we only talked about powers of sine and cosine the last time. So the rules for all the other powers of trig functions, which are not sine and cosine, comprised of this. For combinations of tangent and secant and cotangent and cosecant, you can either leave a factor of secant squared or cosecant squared for your du, and your u will be tangent or cotangent. Or you can leave a factor of secant tangent or cosecant cotangent for your du, and u will be secant or cosecant. It depends on whether you have odd or even powers. So for instance, in example A, I see I have cosecant to the fourth x, cotangent to the fourth x. Well, easily I can see that cosecant to the fourth x can be cosecant squared x times cosecant squared x times cotangent to the fourth x dx. I know that that's almost the derivative of cotangent, and I can make that cotangent. So this can be cosecant squared x. Cosecant squared x is cotangent squared x plus 1. And then we have cotangent to the fourth x dx. So, if u is cotangent x, then du would be negative cosecant squared x dx. So the only thing I have to count for is that negative. So I would have a negative the integral of du, I'm just doing it in order because I can, u squared plus 1 times u to the fourth. So when I integrate that, that's really, if I distribute, it's negative the integral u to the sixth plus u to the fourth du. So that's really negative u to the seventh over 7 minus u to the fifth over 5 plus c. And u is cotangent, so that means this is negative cotangent to the seventh x over 7 minus cotangent to the fifth x over 5. Don't forget the cupcake. So it becomes relatively easy when they're both even. Now when you have an odd and even, that's when it makes sense to leave a secant and a secant and a tangent, or a secant, cosecant and cotangent alone for your du. So let me change color so you can see the difference here. So I could rewrite this as secant squared x times secant x tangent x dx, and that can be my du if u is secant x. So if u is secant x, du would be secant x tangent x. So my problem simply becomes u squared du, and the integral of that is u cubed over 3 plus c. Don't forget to go back and put it in terms of the correct trig function, which in this case is secant. So we'd have secant cubed x over 3 plus c. Okay, so when they're both odd, you can leave a power of each and then change to secant or cosecant. If they're both even, you can leave a power of cosecant or cosecant squared or secant squared. And if you only have one power, you can change it so that you have both. So for instance, if I have secant to the fourth x dx, I can rewrite that as secant squared x dx times secant squared x dx. Well, that's a convenient du, but it's not a du for secant. But I can change secant to be tangent squared plus 1 with my Pythagorean identity. So now, if u is tangent x, du is secant squared x dx. So this just becomes u squared plus 1 du. So if I integrate that, I get u cubed over 3 plus u plus c. So remember, u is tangent, so that would be tangent cubed x over 3 plus tangent x plus c. Okay? And the same thing could be true for cotangent. So I could rewrite that as cotangent squared 5x times cotangent squared 5x. And I know that the derivative of cotangent is negative cosecant squared. So I'm going to change this cotangent to be cosecant squared 5x minus 1 times cotangent squared 5x dx. Still not really finished yet because I still need to distribute this cotangent squared. Sorry, hang on a second. Yes, I have to distribute that cotangent squared. So that would give me cosecant squared 5x times cotangent squared 5x minus cotangent squared 5x dx. So I'm okay for this part because u could be cotangent and du would be cosecant squared, but I can't do this yet. So I need to change that cotangent squared to cosecant squared. So this first part stays the same. Cosecant squared 5x cotangent squared 5x minus cotangent squared would be cosecant squared 5x minus 1. And now all of that's dx. So I can integrate now. I kind of use a u substitution on this one. So here the u is cotangent 5x, excuse me. So du is negative 5 cosecant squared 5x dx. So that means I have to have a negative 1/5 integral u squared du. So that would be negative 1/5 times u cubed over 3 plus c. So that's this part. When I integrate cosecant squared of 5x, that's just cotangent, but I have to deal with, well, actually it would be negative cotangent, but I have to deal with the 5, so I need a 1/5. And then when I integrate 1, I would just get x. So I get the answer to this integral problem, negative cotangent to the third of 5x over 15, so that comes from here, whose derivative is cosecant squared would be negative cotangent, but because there's already negative there, that would be plus, and I need a 1/5 to undo the angle, so that would be cotangent 5x, and when I integrate what would be positive 1, I'll have plus x plus c. That one's a little more complicated. You have a lot more algebra to work in there, and so that can happen, and you may have to play around with them some. Now, what I will tell you is that this last example that I have on here is a little bit of a trick, because if I rewrite secant to the 5th as secant cubed x times secant squared x dx, I know that I can change that to tangent. I know that I could write this as secant x times secant squared x times secant squared x dx. So both of those could become tangent squareds, but that doesn't really help me because I get this extra secant. So what I will tell you is that this particular problem leads into the next type of integration we will go to, which is integration by parts. So just kind of a preview as to the type of problem that will happen when we run into that situation. So I thought it was worth talking about. So bring any questions that you have on the notes to class tomorrow, and I will see you then.